In the previous video, we started writing time complexity functions for a variety of small algorithms, and now we want to talk about the size of this time complexity function. So we argued that a constant time complexity function has a constant order, really. The number of operations will be 25 regardless of the input size. But in our example 2, because we had a nested for loop, we ended up with a quadratic function, which as n gets really large, the time complexity rapidly increases. One of the trade-offs, as time complexity rises, what that imposes is that when we are running this for very large inputs, it may take our machine, our computer, a very long time to process that function and to provide an output. So we want to classify a function in terms of its order. So the order based on the structure of the time complexity function, this leads us to describing its order. For time complexity functions with only one term, for some constant c and input variable n, we'll talk more about this soon, we can describe the following orders. So if your time complexity function is a constant, we say that it's constant order. And we usually write that with this big O notation. We won't get really heavy into the mathematics of the big O notation, but we would write that the order of a constant is 1. We'll get back at why we say this is 1. 1 is sort of the base constant. And all of these orders are going to be described in terms of the base constants. So if your time complexity is some multiple of n, that's a linear function right there, and that's called linear order. And linear order is, again, order of a constant times n is just written as n. Again, n is the simplest linear function you can have. C times n squared is quadratic order, and we write that as big O of Cn squared is n squared. Again, we just remove the constants because we just want to know, is it quadratic or not. If it's c times n cubed, it's cubic order, and again, it's big O of Cn cubed is n cubed. The constant really doesn't bother us because if you think about it, constants, even if they're scaled up, do not have an impact on the time complexity as n gets sizably large. They both blow up into cubic order regardless of what this coefficient is. And then if it's c times log of n, it's called logarithmic order. Written big O of c log n equals log n. Again, we just remove the constant. C times n log n is, I guess we could call this like linear logarithmic order, but we'll just refer to it as logarithmic order. And written big O of c times n times log of n is n log n. Again, removing the constants. So here you could have something like 3 times 2 to the n, that's exponential order. And we write big O of c times b to the n is b to the n. So what I've provided down here is a graph of these various functions. And what we want to emphasize here is certain functions will grow more rapidly than others. So in this, we actually have arranged from fastest to, or most efficient to least efficient. So I'm going to write that right up here. We'll say that this is the most efficient to the least efficient. Well, what do we mean by least efficient? That means we're going to have, for the least efficient ones, Tn is going to blow up much faster. So Tn is going to be really huge here for large inputs, but Tn is going to be typically pretty small here for large inputs. So when we take a look at this graph, we see that the purple function, so let's think about the x-axis as the input size. So that, remember, is the value that is affecting the time complexity. That is the thing that is going to determine our time complexity. And then T of n is the total number of flops based upon that input size. So in our 2 examples, those input sizes were perhaps the number of times a loop would run, or in example 1, that value of n was really never used other than to determine whether the if statement would execute or not. So you can see that the purple function here is the most efficient And what we mean by most efficient is in the long run. So when you start to increase your input size, we call this in the long run, because typically we are not running functions for 2 iterations or 3 iterations. In the real world, things run a lot of time, maybe millions or on the order of millions of times. So we can see that although there's some weird stuff going on here where maybe there's one of the curves is lower than the other curves, what we can determine for sure is that this guy here is the logarithmic order. So this is the most efficient, because even as n gets sizably large, the number of operations, notice, is well below 5, even for 10 or 11 operations or iterations of a loop. We can see that the next most efficient, as n gets increasingly large, is this black one here. And that black one is logarithmic, or I'm sorry, I have these mixed up. This right here should be x log x, and this right here should be x log n. Scratch that, I can't read my own graph. So you can see that as n gets sizably large, even though the linear function is less efficient than the black function, eventually there's a crossover here. And that's really what we're looking after, that as n gets larger than 10, the red function requires fewer operations than the black function. We can see that here, that this output value right there, for example, is smaller than that output value right there. And what do we mean by output? We mean the number of operations. So perhaps this one requires almost 11 flops, but this one only requires about 10 flops for an input size of 11. So this was okay. And then you can see that there's a huge discrepancy. So the x log x, or n log n, if you want to use n instead of x, it performs worse in the long run than a linear function. A quadratic function, you can see that's the blue one, performs sizably worse than any of the other 3 functions that we've considered so far. The green function, which you'll notice is the third or second to last, that function falls below the red function, that is y equals x cubed. And the exponential function, 3 to the x, you can see ultimately goes above the green curve, and that is the least efficient of all of these. So you typically do not want to write functions of exponential order. You would prefer to have something that stops right about here if possible. Quadratic order still behaves pretty nicely, but then when you get into cubic, things blow up very rapidly, and by the time you get to exponential, those are some messy functions, and they do take some time for your computer to run them. So this helps us in the following way. Why would we want to talk about these different orders? Well, a lot of times our functions, our time complexity functions, has a combination of terms, some of which are linear, some of which are quadratic, perhaps even exponential. Then the order of that time complexity function is the order of the most rapidly increasing term. Why? Because terms that grow faster than others will dominate as the input size n approaches infinity. That is, we mean gets very large. So we're doing this long run analysis. There are other analyses that, maybe in the short run, if you're planning on just running a couple loops and you really want to optimize your code, you could come back here to this graph and you could argue that, well, I'm okay with cubic order as long as n is less than 1. That's better than the linear function y equals x. But again, we're operating in the long run as n gets sizably large. So here's another example. What is the order of t of n equals 100n plus 2 log n plus 0.001 times 2 to the n? The coefficients do not really matter. At first attempt, we might think that this term is going to be the dominant term, but this is a linear term. This is linear. This next term is logarithmic. And this next term here, this whole thing, this is exponential. And so in the worst case scenario, the order of 100n plus 2 log n plus 0.001 times 2 to the n, the order of this whole thing is 2 to the n. That is, we can describe this as follows. This algorithm algorithm has exponential order. Okay, so if for very large n, you are going to see this whole function behave like an exponential function. Let's actually take a look at how we can visualize this in a graph. So you can see here, this red function right here is actually a graph of the 100n plus 2 log n plus 0.001 times 2 to the n. And at first, it looks fairly linear. It seems like that 100x is having a pretty big influence because as x approaches 1, as n approaches 1, I should say, we see that this requires about 100 operations, which tells us that this 100x is having a major contribution to determining that because 2 times log of 1 is really, really small, and 0.001 times 2 to the first is very, very small. So in the short term, this 100n is affecting the shape of this graph. But as I begin to zoom out, watch what happens. Suddenly, eventually, this graph becomes exponential. So we see that 100n is having some influence in the beginning shape of this graph, but as n gets sufficiently large, it starts to behave like more like an exponential. And in fact, if I plot 2 to the x, which we're saying that this function has that order, watch what happens as I zoom out really far. The behavior of the red curve mimics that of the blue curve. Now there's a little bit of a shift between them, but if I were to shift this over just a smidge, let's see, x minus, if I were to shift this over, so I'm doing a horizontal shift here, let's see how far I have to shift this over. Whoops, I want to do minus 20 there in the exponent. Let's try 20, maybe 10, there it is. So if I shift this 2 to the x curve over to the right 10 units, you can see that in the short term they look very different, but in the long run the blue curve and the red curve behave almost identically. And that is why we say that the time complexity of this whole expression is exponential. So in the long run, it behaves like an exponential function.